Thank you, Rob. It's certainly a pleasure to be here. It's my second time, I guess. So what I want to talk about today is joint work with two of my graduate students, Christos Trampoulidis and Ehsan Abbasi. And I'm going to talk about lasso with nonlinear measurements. So this is a simple talk. I should be able to finish in half an hour. I came in on a red eye last night, so if I'm incoherent a little bit, that's the reason or my excuse. But it's a simple enough talk. I should be able to get the main idea across. And I'll also use this talk as an excuse to talk about something else or to introduce something else. Okay, so here's the outline. I'll start off with a brief introduction. And so the basic problem is looking at trying to recover structured signals, but using nonlinear measurements. And so a very typical example of this is when you do quantization. So you have some measurements, maybe it's a linear measurement operator, but you're quantizing them to some number of bits, and so you're adding nonlinearity there, okay? And so we'll look at a particular way of trying to reconstruct the signal with these types of measurements, which will appear to be very simplistic, but actually works quite well. Turns out there's classical work going back to Brillinger using, essentially employing the ideas that I'll talk about, and I'll say what he did. This work goes back to the early 80s. And, I'm talking here about prior work, and, prior means, it's causality. It could be even an epsilon time away. And so earlier this year, there's a paper by Plan and Verschinen on the same topic, and I'll talk about that. Then I'll give the main result, which essentially relates employing the lasso algorithm to the situation where you have nonlinear measurements and relating the performance of such a scheme, if you will, to standard lasso with suitably adjusted linear measurements. And I'll say a few words about what the consequences of this are for quantization and how one can design optimal quantizers, say, if you want to use the structured signal recovery methods we'll talk about here. I'll kind of try to outline the proof. And, during outlining the proof, I really want to bring in the other thing, which I think is more important than the talk itself, but to introduce to you a certain extension of a lemma of Gordon, and then I'll conclude. Okay, so here's the setting, preaching to the choir. So we have a unknown signal X, which is structured. And structure here could mean whatever you want. It could be sparse. This could be a matrix or a vect version of a matrix. So you could have a low-rank matrix, a block-sparse signal, whatever you want. And so we want to recover this signal from a set of measurements or a collection of measurements, a vector of measurements. I'm going to assume there's always m of them. So n will always be the ambient dimension. M for measurements will be the number of measurements. The only twist is that I have nonlinear measurements. So I think of having some linear measurement matrix A. Think of AI as being its ith row. So I take the inner product, if you will, of a row of A with my unknown vector. Those are the standard, if you will, linear measurements. But then I hit this with some nonlinear function gi. And gi can be possibly random. And certainly it's going to be nonlinear. Okay? So in practice, if you think about this GI could be used. You might have measurement devices that inherently have nonlinearities, or they might have uncertainties, which you will model in some form as some kind of randomness. So G could certainly model that. But more interesting often is the case where these G's are introduced nonlinearly by design. And the classical example of that is, of course, as I mentioned, quantization. And so, for example, if you have noisy 1-bit quantized measurements, what that means is you hit your unknown vector with a row of the measurement matrix A. It's noisy, so there's measurement noise Z. And then if it's 1 bit, basically the information you give across is the sign of this signal here. Okay, so either +1 or -1. That's 1 bit. And the reason why I put an I here, this can potentially be time varying and random. You can see here it's because for each measurement we have an independent noise. Okay, so this nonlinear function can depend on I and it can be random. Okay, so what about prior work? So it turns out that as early as 1982, Brillinger had looked at this problem. In those days, people didn't care about structure as much, so let's take the unstructured case. So just some unknown vector x naught. And so to recover such a vector, we need at least as many measurements as the ambient dimension or the number of unknowns. And so let's assume that. Throughout this talk, without loss of generality, to simplify my formulas, I'll assume the norm of this unknown vector is 1. If that's not the case, then we'll just normalize. I mean, there's no loss of generality in assuming that. And so Brillinger said the following thing. He said, let's just naively, attempt a standard least squares solution to this vector of nonlinear measurements. In other words, I'm going to ignore the fact that these are nonlinear measurements, and I'll put them in a standard least squares type setting, and I'm going to minimize this over x. And of course, as we know, the solution is just the pseudo-inverse times this vector. So you take the pseudo-inverse of A, you multiply it by this vector of nonlinear measurements. So he said, let's do that. Now, this seems, one would be, it appears, naive to assume that anything like this could work. But it's quite remarkable that it actually does. So Brillinger was able to show the following result. Okay? So for his result, and I apologize, I wrote these last night in the plane. That's an E. So if you take the entries of A to be IID standard normal, so 0 mean unit variance, and if you define two quantities, mu being the expected value of gamma times gi of gamma, these nonlinear, possibly random functions, gamma here is again standard normal. So even though these guys can vary with the measurement, I want this particular expectation to be independent of I. And secondly, sigma squared is this quantity here. Again, it should not depend on I. If I define these two things, then what he showed is the following thing. That if you fix the number of unknowns, the ambient dimension, and if you let the number of measurements run to infinity, then and if you look at the estimate you get, the x hat you get, it's actually a good estimate, perhaps not of x naught, the unknown x naught itself, but of a scaled version of it scaled by this parameter mu. And in fact, you can explicitly write down what the squared error will be. It's n over m times sigma squared, where sigma squared is found from this. Okay? So this is for fixed n and m growing, and this holds almost surely. And so this is very nice, because it says, even though we're doing something very naive, as we get more and more measurements, we get a better and better estimate of x naught. Again, modulo this scaling, which of course, if you know mu, you can unwind. Okay. Now, as I'll talk about it in a moment, so we kind of strengthen Brillinger's result, and so let me just tell you how that happens. So in Brillinger's time, people usually studied the case of n fixed and m going to infinity, and so that's his result. Nowadays, it's more customary, to look at the regime where the number of measurements and the number of unknowns is proportional, and so let me assume delta is fixed, and I'll let m go to infinity. And so a special case of our result, when you specialize it to this setting, gives you this formula here. So delta, recall, is m over n. And so clearly, if n is fixed and m grows, this recovers back Brillinger's setting. But it's more general. Okay? Now, very recently, as I said a few months ago, there was a paper by Plan and Vershinin where they take Brillinger's setting, and rather than just optimize arbitrarily over this unknown x. So again, it's the same setting. We have nonlinear measurements. They restrict x to be in some set k, and not even necessarily convex. And they ask the question, if I solve this problem, how good is the estimate I get? And the result they show is the following. So again, x hat is the solution to this problem. Mu is the same mu we had earlier. And so it turns out the 2 norm of x hat to the scaled version of the unknown has this bound here, provided the number of m measurements is bigger than this quantity here. This quantity, for those of you who know, it's the squared Gaussian width of this set when observed from a particular point. If you don't know what it is, it doesn't matter for the purposes of this talk. But it's something that you can compute, and that's the relationship. And there's a third parameter that they need here, which is this psi, which again is this particular expectation. Okay, so this is very interesting, because it says, let me actually say it explicitly, So the reason why you would introduce a setting like this, some kind of set, is to impose, knowledge of the structure of x naught that you might know. So for example, if x naught is sparse, this set would be something like the L1 ball, or a scaled version of it. And so typically, if x naught is structure and the set K is chosen appropriately, and if the point you're looking for is on the boundary of this set, then it often turns out that this squared Gaussian width, I guess Joel calls this the statistical dimension, is strictly less than n, and so you can recover the signal with fewer than n measurements, which is why we're all here. And so a strength of this result is it's not asymptotic, unlike Brillinger's. A weakness is that it's not as explicit as, or tight, if you will, as Brillinger's. There's this, constant c, which is really not telling you how tight this is. Okay, so how does our work relate to this? So similar to Brillinger, our work is asymptotic, but the result is tight. It's asymptotically tight. And it makes very explicit, as we'll see in a moment, the role of mu and sigma. And so the appearance of the psi parameter that plan inversion had really is artificial. It's an artifact of their proof. And in addition to the constrained lasso that they study, we actually study regularized lasso too, and I'll talk about that. But specialize the plan inversion in setting, our result says the following. So we need to assume this set is convex for our result to go through. If you fix, again, the ratio of the number of measurements to ambient dimension and fix the ratio of, if you will, the statistical dimension to the ambient dimension to rho, then this is the result. Okay, and as I said, it explicitly shows that things just depend on mu and sigma squared. Okay? Now, as I said, we will be studying generalized lasso. So for signal recovery, we'll be looking at this algorithm. So there's a least squares part to the cost. And then you add to it your regularizer. F from now on will be a convex regularizer. It's put in to encourage the structure we're looking for. So an L1 would encourage sparsity. As we know, nuclear norm encourages low rankness. An L1, mixed L1, L2 norm encourages block sparsity. An infinity norm would encourage, say, constant amplitude signals such as BPSK. And the list goes on. Okay, so here's the main result. So again, we're going to assume that the measurement matrix A has IID standard normal entries. Without loss of generality, the 2 norm of the unknown I'll take to be 1. And I'm going to look again at this squared error. So the squared error between x hat, the solution to the generalized lasso when y is replaced with these nonlinear measurements, to the scaled version of the true x naught. Okay? And so it turns out that this squared error, whatever it is asymptotically identical to the squared error that you get if you solve generalized lasso not with these measurements, but with linear measurements of this form, where AX naught is scaled by mu, and you have an additive noise term with variance sigma squared. And mu and sigma squared are as before. Okay? So what this is really saying is that if you want to understand the performance of generalized lasso when you apply it to nonlinear measurements, all you need to know is study the performance of standard lasso for these linear measurements, just appropriately scaled and with noise added to them. So that's the result. Okay? And so the first bullet is what I've said earlier. Now, why is this interesting, at least for us? Well, recently with Oymak, my former student, and Christos, we have developed a methodology where we can analyze lasso with linear measurements, and I'll talk a little bit about that. And so that allows us to analyze things here. And if you go through that analysis, you get this hairy-looking expression, essentially saying that, and I apologize, there should be a mu here, that the squared error, alpha squared, is given by the solution to this scalar optimization problem. So it's scalar because there's a tau and an alpha, and that's it. M and n are the dimensions. Alpha is what we're looking for. So the only mysterious thing is this proximal operator here. We heard about it earlier, I guess, in Volkan's talk. So this is the proximal operator of actually the Fenchel conjugate of F, and I'll talk more about this. But so if you can compute this thing, and then often, depending on what F is, this can often be done, and this thing often concentrates. H here has IID standard normal entries. So this ends up concentrating to something deterministic often. So this is easy to do, even though it looks hairy. And so, for example, if you look at the one-bit quantization problem that we looked at, so we have AX naught, linear measurements, we're quantizing to 1 bit. It turns out in this setting, mu and sigma are easy to compute. These are the values. And here is the performance. So what I'm showing you here is the squared error in recovering the unknown signal as a function of lambda. This is the regularization parameter. And I'm doing this for a problem where the ambient dimension is 768, the signal is 115 sparse, and I'm doing 2 sets of measurements. One where the number of measurements is bigger than n, 920, which is this setting here, and one where it's less, but still above 115. And this is actually noisy one-bit quantization. So I'm taking my observations and I'm also adding noise to it. Okay? And so this is just showing that everything works. So the squares, I guess, are the simulations we get when we actually apply nonlinear lasso and then empirically compute this. I guess this funny-looking star is the result you get if you solve the equivalent linear one. And the blue curve is the theory, essentially plotting out this curve, which you can explicitly do. Okay? And so the theory very well matches the empirical evidence, and the linear and nonlinear guys match very well. And so this is useful because once you have curves like this, it certainly tells you things like how to choose lambda and so on. So that's one-bit quantization. We can look at qubit quantization. And so if you look at qubit quantization, the question there is that if I have qubits of budget to quantize, how do I choose the quantizer? How do I choose the intervals? And how do I choose the quantization values? All the results I've described, whether they were Brillinger's or Plan Verschonens or R's, suggests that what you should really do as your estimate is not x hat, but 1 over mu times x hat. And so this is really the squared error that you want to look at. And so if you look at Brillinger's result, or our result in Brillinger's setting, if you will, this is what the squared error is. And so what you really want to do to minimize the squared error is to choose your quantizer to minimize the quantity sigma squared over mu squared, because it's this quantity that depends on g. You have control over this. Okay? Now, in the generalized lasso case, we don't have as explicit a formula, but it turns out you can show that, again, the squared error is an increasing function of this quantity. And so what you want to do is to minimize this ratio. And I won't go through the details, but what's interesting is it turns out that the quantizer that minimizes this ratio is the famous Lloyd-Max quantizer for Gaussian random variables. Okay? And so this is important because it says the best quantizer to use is what people have already been using, and it doesn't depend on m, n, or the structure of the signal. What happens if I? No, with prior it's the same thing. So this result, so by prior you mean the F? So this is still true. So this result that I'm saying, even for generalized lasso, which brings in your regularizer, your F, nuclear norm or L1 norm or whatever, it turns out that the squared error is an increase. It's a more complicated function, but it's an increasing function of this ratio. And so that's what you want to minimize. And minimizing this, it turns out, is done with a Lloyd-Max quantizer, which minimizes the squared error, if you will, for Gaussians. Okay? So I think that's an important result. How much time do I have? No time? Oh, 10 minutes. Okay, so I can. Then we'll see a little less of the proof. So that's basically the bottom line of the result. I want to give you an outline of the proof. And so this will be an outline, and so I'll be hand-waving. And if you hold a gun to my head, then I will recant everything I said about this proof, but it's just an outline. Okay. Now, what we use for the proof is the following lemma, and I'm using this talk as an excuse to introduce this lemma because I think it's more important than the talk itself. And so let me describe what that is. So this is a generalization of a lemma of Gordon from the 80s called Gordon's Gaussian comparison lemma, I guess, but it's a generalization. I'll talk about that. Okay? So I'm going to look at two optimization problems. The first I'll call a primary optimization problem, PO, which is the following. So it's a min-max problem. I'm minimizing over a variable x living in some set S of x and maximizing over another variable y living in some set S of y. And the objective is this bilinear thing in x and y. So there's a matrix G sitting here, and then some fixed function of x and y. Okay, so this is the primary optimization. And in this setting, I will always think of this G as being a matrix with IID standard normal entries. Okay, so think of G as being like that. And then I'm going to have an auxiliary optimization, AO, which is a phi of little g and h. So note here, when I do this min and the max, the only thing that remains is g. So the capital phi is a function of g. Likewise, the little phi is a function of two vector g and h's. Again, these vectors I'm going to think of having IID standard normal entries. And in the auxiliary optimization, I keep the same psi, but I replace this bilinear form by the inner product of this Gaussian vector with y scaled by the norm of x. This is a 2 norm. And the inner product of h with x, another IID Gaussian h, again, this time scaled with the 2 norm of y. Okay? So that's the auxiliary optimization. Now, why is this useful? Well, so the theorem has 3 statements. The first statement is the following. So it says the probability that little phi is upper bounded by c times 2 upper bounds the probability that capital phi is upper bounded by c. So recall or note that phi and little phi are random variables. They depend on g, capital G, little g, and little h. Okay? So this is very similar to Gordon's statement for those of you who know what that is. But why is this interesting? This is interesting because what it says is that if you have a good lower bound on little phi, on this auxiliary optimization, you have a good lower bound on the capital phi. Because if this probability is small, so if c is a good lower bound, the probability of phi being less than c will be small, and so by fiat, the probability of capital phi being less than c is small. And so if you have a way of analyzing the auxiliary problem and providing a good lower bound, you automatically have a good lower bound for phi. Okay? So this is an interesting result because I've said nothing about the function psi, and I've said nothing about the sets Sx and Sy. So it's a very strong statement in that sense. It's also a weak statement because it doesn't say a whole lot because I haven't said a whole lot about Sx, Sy, and Psi. Okay? And so if I say more about these sets in this function, I can say more. And so if now I assume Sx and Sy are convex, at least one of which is compact, and if I assume this function is convex concave, then you might not be surprised that I can do some kind of duality argument and then show the following result. So this says that if little phi is within some epsilon neighborhood of c, so the probability of this event, upper bounds the probability of the event that capital phi is within some epsilon neighborhood of the same c. And so in particular, if little phi concentrates to c, so if this probability is small, capital phi will concentrate to the same value. This probability is also small. Okay? So we can actually, through solving or analyzing the auxiliary optimization, figure out what the min-max value of the primary one is. But most importantly is the third statement, which says something about the solutions. Okay? So I need one more assumption. So if I look at the primary optimization, and I look at the minimization over x, okay? So it's a convex optimization because for any value of y, this is linear, this is convex in x, and so you're minimizing a convex function. And so if I look at the maximum of these functions, the maximum of convex functions is convex, and so as I said, it's a convex optimization. But if in addition it's strongly convex, so that's the additional requirement, and if this little phi concentrates, then the following is true. If for any norm the solution to the auxiliary problem concentrates to some value, the norm of the solution to the primary will concentrate to the same value. Okay, so you can learn something about the norm of the solution of the primary from the norm of the solution of the auxiliary. And this is remarkable because these two problems are really not related. You know, this one depends on a little g and a little h. This one depends on an independent capital G. So the solutions are never the same, but under these conditions, the norms are. Okay? And so this is really what we use for these proofs. Do I have 3, 2, 3, 1 minute? 2? Okay. So I can't give you the details. I can just walk you through it. And so the way we use this result is the following. So let's look, for example, at this optimization. So I'm minimizing over W, AW plus Z plus this term here. A has IID Gaussian entries. Z, let's suppose, has IID entries, but an arbitrary distribution, and Zi squared has expected value sigma squared. So Z is not necessarily Gaussian. Okay? But it turns out we can analyze this problem. The way you do it is you take the 2 norm, and I apologize, this should go the other way around, write it as the maximum over u's whose norm is less than 1 of this bilinear form. So there's a bilinear form. A has IID Gaussians. And so this is the form of a primary optimization. This whole stuff here is like your F. It's linear in U, hence concave, and it's convex in W because F is. And so you can apply your auxiliary optimization problem, which, if you recall, has this form, and you can analyze it, which I won't do because I don't have time. But the bottom line is that when you analyze it, it turns out that the norm of the solution here concentrates to a universal value which does not depend on the distribution of this Z. Okay? So the Z can have any distribution. W will converge to some universal value. Now, why is this useful? Because if you look at the nonlinear setting that we have here, so nonlinear lasso is this thing. Okay? Now, my error is mu x naught minus x. So I'm going to write everything in terms of this error W. So I replace x with W minus mu x naught. That's this thing here, over here as well. Okay? Now, if you look at this quantity here, Z, it's not difficult to see that it has IID entries because AX naught, each, you know, if you look at this thing, each row is independent. When it multiplies X naught, it gives you an independent value. So each entry of this vector Z is IID. And it's not too hard to show. Again, I'm not going through the details, that this thing here, even though it's not Gaussian, it's almost independent of A. I'm skipping that stuff. And so given that it's almost independent of A, so this is the Z, then I can appeal to the theorem that I had earlier to say that the squared error, say, of W, the norm of W, is the same if I replace this thing with an IID Gaussian, which is the linear set. Okay, so that's kind of the very high-level way of doing the proof. We can also use this lemma to compute the squared error. Again, I don't have time to go into it. So you look at, again, the linearized lasso. So I want to figure out what the error is. There's no equal sign here. Again, what you do is you take the 2 norm and you write it as the maximization over a U that has norm less than 1 to get a bilinear form. You turn this into an auxiliary optimization problem. And then you beat that to death. I don't have time. So there's 3 slides that just went away. It gives you the proximal operator of the Fenchel conjugate and the result that you want. It's just massaging the auxiliary optimization problem, and you get these types of results. So basically, to summarize and conclude, we looked at the problem of structured signal recovery from nonlinear measurements, but using an algorithm that's suited for linear ones. This was first studied by Brillinger, and then recently by plan inversion in, but I think we've kind of settled the issue here. So we've shown that the performance of these methods is equivalent to one with linear measurements. The result is asymptotically tight. It improves earlier results, and it shows the optimality of Lloyd max. And the proof relies on this generalization of Gordon. So I'll stop here. So the rows are independent and rotationally invariant. So by comment, you mean whether these extend to that setting? Is that what you mean? Right, right. So that I don't know. If it so here we pretty much we're talking about things that you and I know well. So it has to do with this universality. So I don't know the answer to that. But whether just rotationally invariance is even enough for what we have here, I suspect it is, but I have to think.
So it's not so much a question about the analysis, it's a question about the methodology.
No, so that's what I'm saying. So the methodology I described here for the proof,
Not the methodology for the proof, the methodology for recovering the structure.
yeah, you would do the same algorithm, I think. I wouldn't bet my life on it, but I would wager on it that the analysis I described will go through if you have rows that are independent and rotationally invariant. So the question is, if the measurement matrix is deterministic, it's not drawn from the Gaussian ensemble, whether these results are true and whether the Lloyd max quantizer is optimal. I don't know. I suspect that, there is some kind of universality here. But I don't think if you have an arbitrary deterministic measurement matrix A, that the guarantees here and the optimality of the Lloyd max quantizer are true. I still think if you do this, you'll get some reasonable estimate of your signal, but I don't think the guarantees will extend to an arbitrary deterministic A.